The information that's reported in the first 5 columns of the spreadsheet represents data for 20 countries taken from the UN Development Program database for the year 2015. The first variable is average life expectancy at birth, and that's measured in years. In column C is the percent of the population that resides in an urban area, and that's X sub 1 for this model. In column D is percent of GDP that's devoted towards public health expenditures, and that's variable X2. And the last variable in column E is the average number of years of education for a population. What we're going to do is use these variables to estimate a multiple regression model. If you have not already done so, watch the video first where I demonstrate how to use the LINEST function for estimating a bivariate regression model. In that video, I show you the formulas that are used for computing hypothesis test and confidence intervals that I will demonstrate here. And I go through the process of constructing then the output, as you'll see here in a moment, a little more slower fashion and more detail. But let's go ahead and demonstrate how we can use the LINEST function in Excel for generating a multiple regression model. The first thing that we want to do is we want to determine how many independent variables we have. And right now we'll have 3 independent variables. We're regressing life expectancy on urbanization, health expenditures, and education. Add an intercept to that, and what that means is we'll have 4 columns of information to report. 1 column for each of the independent variables plus the intercept. But we also need to go down 5 rows. So click model and drag where you want your output to be deposited. I've already picked a place and I've already added labels here so that make it easier for us to quickly go through what the output is. Once you've highlighted the data, the cell range where the output from the LINEST function is going to go, what we're going to do is use the equal LINEST function, open parenthesis. We're going to go over and find the array of known y's. That's the y variable, comma. And now we want to identify where the known x's are, comma. And then what we'll do is there are 2 more options. One for an intercept or a constant, which I always generate, comma. And then also the last option is for generating a variety of statistics for the regression model, and close parenthesis. Avoid the temptation to immediately press the enter key, because what we'll see here is LINEST is actually an array formula. Because it's putting output into more than one cell, it's more than one piece of information that it's generating. That's why we had to identify a range of cells for it to place the output into. So for entering an array formula, hold down the Control and Shift keys, and while those are being held down, then press the Enter key. And there we see the output as it's generated. You'll notice then that when we look at the output, what's really odd about the LINEST function is that it reports the coefficients in reverse order in which we entered them in the spreadsheet. To refresh your memory, you notice X1 is in column C. To the right of that is then X2. To the right of that then is X3. But the way it reports the results, the intercept is in column L. To the left of that is the coefficient in standard error for X1. To the left of that is the coefficient in standard error for X2, and to the left of that then is the coefficient and standard error for X3. So a little odd that they have chosen to report the results in the reverse order that they are actually entered in the spreadsheet itself. But we'll see also, in addition to the first 2 rows that contain the coefficients and standard errors for each of the 3 independent variables in the intercept, there's also model information that's contained in the 3 rows that are below the standard errors and coefficients. We see the R-square value, the F statistic, model sum of squares, oftentimes referred to as the regression sum of squares or explained sum of squares. Then next to that is the residual sum of squares, often sometimes referred to as the error sum of squares. Above that, degrees of freedom, which is n minus k minus 1, where n is the sample size. K is the number of independent variables, in this case 3, and subtracting 1 from that for the intercept. So 20 minus 3 minus 1 gives us a result of 16. And then above that is the standard error of the regression, also sometimes referred to as a standard error of the estimate. What we're going to do is take this information that we have here and we're going to put it into a tabular form that is more consistent with what you see that is generated by most statistical packages. Now, while it looks like there's only some information that's contained in this output, there actually is everything there that we need for generating an F statistic and also for generating T statistics and confidence intervals for this regression model, and I'll show you that in just a moment. Now, below the urban and intercept standard errors, you notice that pound n/a. Well, in those 6 cells, there is no information that's reported. So don't think that you've done something wrong. The model information is always reported in those first 2, or the columns rather, of the output. And so there's nothing else to be reported once we get to the right of the standard error of the regression, the degrees of freedom, and the residual sum of squares. Okay, now let's go through the process of actually completing then these tables. First of all, for the regression sum of squares, or the explain or model sum of squares, it's reported right here in this cell. The residual or error sum of squares is reported right here in this cell. The total sum of squares then is nothing more than the regression sum of squares plus, of course, the residual sum of squares. The degrees of freedom for the regression, or for the model, refers to the number of independent variables in the model, which is 3. The residual degrees of freedom here for the ANOVA table is going to be n minus k minus 1. Well, that's already reported in the output for us right there. And the total degrees of freedom is nothing more than the regression degrees of freedom plus the residual degrees of freedom, which, by the way, represents n minus 1. So to find the sample size, just take your total degrees of freedom from the ANOVA table and add 1 to it. The mean square regression is going to be nothing more than the regression sum of squares divided by its degree of freedom. The residual mean square is going to be the residual sum of squares divided by its degree of freedom. And those, we'll see the F statistic, the reason why it's called a ratio, it's nothing more than the ratio of the mean square regression divided by the mean square residual. And that's F statistic value of 5.28. Now, to find the probability value of that F statistic, we'll use the f.dist.2t, or right t rather, RT. And what this is going to generate then for the F statistic value that we have is the area under the curve that falls to the right of 7.285 between that value and a value of 0. The F statistic value is the first parameter we add into this formula, comma, the numerator or the model degrees of freedom, comma, and then the second degrees of freedom, or the oftentimes referred to as the denominator degrees of freedom, is nothing more than the residual degrees of freedom we see in the ANOVA output. And right there is a probability value of 0.00269. So given an F statistic value of 7.285, regression model like the one we've just estimated here, given our sample, likely came from a population where the R-squared value is equal to 0 only 0.3% of the time. So it's highly unlikely then that this regression model with an R-square of 0.5773 came from a population where there is no relationship or the regression model does not explain any variation in y in the population. Now let's go ahead and complete the hypothesis testing that we'll see in terms of this second table. First of all, the value of the estimated intercept and its standard error falls right below that. The value of the coefficient estimated for the variable urban, and then its standard error is right below that value. Then we can easily see the value of the regression coefficient for health expenditures as a percent of GDP, and right below that is its standard error. And lastly, for education, its coefficient, and then below that is going to be its standard error. And right there is the output that you see that's already produced, but this may be in a format that's easier for us to understand and more consistent with what you see stat packages actually generate. Now, as far as the t-test as a test of significance, we're comparing each of these coefficients to assumptions in a population that they were equal to 0. So all we need to do when that's the case is take the coefficient divided by its standard error. The coefficient divided by its standard error, and we'll do that for the remaining two variables as well. And again, all of this in terms of the formulas and the process I've gone through to explain how this works can be found in the bivariate regression tutorial I have up that demonstrates how to use the LINEST function. As far as the probability value, it's going to be equal t.dist.totail. I'm sorry, it's going to be, no, that's correct. Open parenthesis, the F statistic, comma, and then, I'm sorry, T statistic, comma, and then the residual degrees of freedom. And we see the probability value is less than 0.0000. And actually, what I can do very quickly is come up here, and actually I'll just format from this menu here. And what we'll do is format the output here in terms of scientific notation, and we see here that the probability value for a t statistic of 11.19 when we have 16 degrees of freedom is 0.000000565666. So highly statistically significant. Let me go ahead and revert back to the previous format for reproducing the probability. The same process we'll use here for generating the probability values for each of these regression coefficients. I'll take the t statistic for the urban variable, comma, degrees of freedom, which is n minus k minus 1, or 16. Has a probability value of 0.014. So it's the likelihood that we would have drawn a sample of 20 cases from the larger population from which these cases come from, randomly that is, that would generate a coefficient for the urbanization variable of 0.259 with a standard error of 0.094 will occur only 1.4% of the time by chance. Certainly would lead us to reject the null hypothesis at the 95% confidence level, but not at the 99% confidence level using a two-tailed test. All these are two-tailed tests. We'll do the same thing here for the next variable. The test statistic, and then the degrees of freedom. Probability value of 0.09 in essence. So would not be significant at the 95% confidence level, but would be at the 90% confidence level. And then we see again .t dist .2t, two-tailed that represents for 0.13, comma, and of course our degrees of freedom will be the same. And there, it clearly is not statistically significant. So that's how we generate t-statistics and their probability values for a two-tailed test for each of these. Now to generate then confidence intervals for each of these coefficients that have been estimated. It's going to be equal, and I'll take the coefficient itself, since we'll work with the intercept first, minus 2.inverse.2t, and again this is looking for the critical values here that separate off the 5% of the area under the curve that's in the upper and lower tails. The probability value, instead of putting in 0.05, I'm going to use 1 minus 95 divided by 100. What that'll do is take 95 divided by 100 and puts it into proportion of 0.95, subtracts that from 1, which will be 0.05. This will allow me a more flexible formula so I can change the confidence interval value there in cell N14, and it will recompute then confidence intervals automatically. So it makes it rather flexible. Same degrees of freedom we've used up till now, close parenthesis. And what this t dot inverse dot 2t does, it generates then the critical values of t for 16 degrees of freedom, for, in this case, for the 0.05 alpha level. Multiply that then by the standard error. Hit return. And I forgot to mention, but I subtracted then the critical value times the standard error from the coefficient, because that's the lower limit. The upper limit instead would be the coefficient. Adding to that then the critical values for the two-tailed test for t, for 1 minus, again, we'll use the exact same process we did before, comma, and now we identify degrees of freedom, times then the standard error for the intercept. And there's the upper limit for this confidence interval. We'll do the same thing here. Take the coefficient for urban, subtract from that then the critical value of t for an alpha of 0.05 we're using right now at 16 degrees of freedom, and multiplying then that by the standard error for the urban coefficient. And what we'll do here is again take that coefficient, and now we'll add to that the critical values for a two-tailed test. 1 minus, again, 95 divided by 100 will give us a 0.05 probability and 16 degrees of freedom. So that critical value would multiply then by the standard error for the urban coefficient. And there's the upper limit for that regression coefficient's confidence interval at the 95% level. And we'll go through the same process here again. I'm a little bit faster typing these in if I'm not talking and explaining them at the same time. And now let's generate the upper and lower limit values for the confidence interval for the variable education. one last one. I could have just copied what is listed there in for the intercept down, but I just want to go through the process several times here so you can get a sense of what the routine is. I think those look correct. Let me double check just to make sure. Those are lower limits, and these all should be plus after the coefficients. And the only thing that should change then in each of these is the standard error. Yep, they all look fine. Now, the reason why I put the probability value not as 0.5, but instead as 1 minus what's in N14, which is 95 divided by 100, is I can change the confidence level to 90% and recompute all of the confidence intervals with just one push of the button. Same thing for the 99% confidence level or the 99.9% confidence level. But I'll go back to the 95% level. Now for the R-square, it's already reported in this output. For the sample size, I could either just do a count of the number of cases in the data that I have there in the first in columns B through E, or I can simply take the total degrees of freedom and add 1 to that, because that always then will give me the sample size. Now for adjusted R-square, what I'm going to take is 1 minus, parenthesis, 1 minus what is the R-square value. Oops, let me go back here and do that again. I didn't start that formula off with an equal sign. So equal 1 minus, open parenthesis, 1 minus the R-square value, and I just use that cell that's right above it, close parenthesis, multiply that by what is going to be then the total sample size, subtract 1 from that, close parenthesis, divide that then by n minus k minus 1, which actually has already been done for us right here as the residual degrees of freedom. So that makes it really easy for us. Hit return, and there we have our adjusted R-square value. Now going back to this formula, I could have put parentheses around the parenthetical statement of 1 minus I21, and then around including that in parentheses along with L21 minus 1, but I did not because of the order of operations. It works out just fine. But those first two parenthetical statements multiplied together would be the numerator for the fraction here that is subtracted from 1. But it works out just fine the way I have it here. So this is how then we can generate a multiple regression model using the LINEST function in Excel. It really produces an awful lot of information for us. We just need to know what information is where in the output from the LINEST function and how then we can organize it as would be typical for our interpretation or reporting of a regression model from the stat package.